Okay, this exercise is going to look at water quality in the Chesapeake Bay. And so we are going to go to Blackboard here. When you go to Blackboard, you'll see course content. And under the course content, you'll see a folder called water quality. Of course, this might be up higher in this menu. The folder orders can change, so don't be freaked out if you find it at the bottom. Okay, so I'll click on water quality here. And you have the Chesapeake Bay data. So I am going to download that to my CGIS. Just gonna see if I have one in here already. I do have a water quality folder in the projects, but okay, so I'm just gonna make a folder here called Chesapeake Bay. Okay, and that's where I'm going to go download the data. So I'll click on the student data, and then I'm going to navigate to my CGIS. There's my Chesapeake Bay, and I'm going to save it. Alright, it is downloaded. Now I can navigate to that folder, and I can unzip it here. Okay. Sometimes when you unzip files, they create a folder. I don't really need that folder. I don't know why it does that, so I'm just going to take all of these files and drag it into my Chesapeake Bay folder, and then delete this one that it made. I don't need that, because right here is my geodatabase. I see my geodatabase and some geodatabase associated files. Alright, so now I have my data. Alright, now I'm going to open up ArcGIS Pro. And so there's a lot more information here than what is in the DEC dataset, which is one reason why I wanted to use this, because we can do a lot more really interesting spatial modeling, some kriging, spatial interpolation that we just can't do with the other data because it's too sparse and not powerful enough. So the Chesapeake Bay data set is started in 1984, so a long-term data set, and we're specifically looking at dissolved oxygen. Dissolved oxygen is very important because different types of species need certain amounts of dissolved oxygen. So when you start to get lower in your dissolved oxygen, you start to lose some of these species. I mean, striped bass, white perch, yellow perch, those are yummy eating fish and desirable by fishermen, both sport and commercial. So it's important to monitor your dissolved oxygen, or you'll just be left with bristleworm. Okay, so that's what we're going to look at. And when we go through this exercise, we're going to be looking at 2014, 2015. We're going to be doing some charts again like we did before, and we are going to be looking at spatial interpolation, which is a kriging method, and as we go through I'll get more into what that is. Okay, so for now, let me just kind of get my windows here situated. I'm going to get the outline pulled up that you will be provided if you so choose to use it and run through. But the outline, as I mentioned before, also has questions that I'd like you to answer for this week's exercise. So we had the ones with the DEC data, and now we have the ones with Chesapeake Bay, and you will see that there are some questions. When you do your chart here, as we go through, you'll use different colors, but we'll see that it's a step-by-step, and I'll be asking you, like, what is the mean dissolved oxygen 2014 and 15, and then this interpolation we will go through, which basically the rule is that things are closer to each other should be more related. So when we do spatial interpolation, what it's trying to do is it's looking for data that's spatially nearby and using that under the assumption that it must be related to fill in gaps within your data. And so you will use, say, points of dissolved oxygen and try and fill in the Chesapeake Bay area to, say, give a seamless layer of dissolved oxygen for the Chesapeake Bay area. So it's really fun to do. I've used this for creating moose density maps for the state of Alaska. So all right, I'm going to open up a new project. Just go to map, and I'm going to go to my C projects folder, and I already actually have one here called Chesapeake Bay. I'm going to call mine Chesapeake Bay 2 because I'm kind of redoing this. So it's actually just asking me where I'm going to save it. New project location is under projects, and then here is where I put the name. I can never spell Chesapeake right. Bay. For me, it's just going to be my version 2 because it kind of worked on one. Okay, alright, so that's getting set up there. Okay, so now you're going to go and add your data. So C, from you is C, GIS, Chesapeake Bay, and you'll see it's a geodatabase. So a geodatabase is a collection of GIS files. So we're going to add the Chesapeake Bay. We're going to add the dissolved oxygen for now. Just those 2 files for now. Alrighty. We see that we have the boundary of the Chesapeake Bay here. And we have dissolved oxygen. So I'm going to change this Chesapeake Bay, just the symbology, so I can see through it. So all I did is double clicked on it and it brings up the symbology. And now I can see through it and I can see my dissolved oxygen. Let's take a look at that attribute table. Right click and go to attribute table. And you'll see information as far as what watershed it is. That's what these HUCs are. Kind of the crews that collected the data, the program. It has a sample date, and if we hover over the top, we can see that it actually is in fact a date field. So that's pretty cool. So when we go to do our analysis, you know, that it'll recognize that this is a date field. You know, you can make date fields that look like date fields, but they're just text fields, which then doesn't really work when you try to do time series analysis. The depth at which the sample was taken, parameters, dissolved oxygen, DO, and here's our most important column, the measure of value. That's the column that we are primarily going to be using today. Okay, one thing you'll notice when you look at this is there's no column called year, which is kind of problematic. What if you wanted to divide your data up and say look at 2014 and look at 2015? It's kind of interesting that they don't include that. But I'm going to show you a tip and trick to make a year column. So in order to make a year column, we need to divide out this sample date. Since it is a date field, it's very difficult to break apart. So the trick is first we have to create a temporary field that's a text field. And then from that text field, we can extract the last 4 digits, which is the year, into a year field. So it's a 2-step process, but I'm showing this because you might run into it in future data sets. So I'm going to add a field, and let's just call it temp, TMP, TMP. You can just tab to get among those. And let me see, I'll make it a text field, and I'll give it a length of 20. Okay, and then right away I'm just going to add a year field, year, and I'll make it a long, so it's an integer, but it doesn't have any decimal points to it. Okay, so now go up and save your changes. For some reason the table is not editable. I'm checking to see. I don't have it open by any other anything else. Lots of times when you get that error, that means that it's open somewhere else. But I'm looking around and I don't see where it is. Okay, so we'll cancel that and we'll just discard it. One way to get around this is, if this does happen to you, I noticed that this is a geodatabase, so we can get around it by exporting this into a shapefile. So if this is happening to you, right click on it and go down to Data, Export Features, and I'm going to navigate to my folder where I stored my data. So for me that was GIS, Chesapeake Bay, and then I'm just going to put the name here, dissolved, space capital O, 2, and underscore SHP, just so that I know it's a shapefile and not the geodatabase file. So I'm going to call it dissolved underscore O2 underscore SHP, and then it puts the natural extension of .shp, and then hit OK. Be sure you have nothing selected here. Alright, so I'm going to close this one down. Let me try and add the fields to this one and see if this works. So open up this attribute, add a field, temp, and call it text, and have it be a 20. Add a field called year, keep it as a long, and then hit save. Okay, so it allowed us to update the shapefile. Sometimes if you're having problems with certain applications, sometimes they want shapefiles, sometimes they want geodatabases. You know, that can be a little tip or trick, alternating back and forth between those different types of GIS data sets to overcome issues that may arise. It's rather weird. So I'm just going to remove this other dissolved oxygen so I don't get confused. Remember, one of the rules, first day, was keep your table of contents clean. Alright, so now let's look at our table of contents. And our whole goal was trying to get this sample date, and we want to extract the year. So I'm going to go to the end of the database. You can click on these, and if you click and hold and drag, you can move these fields. So I'm going to move this over towards where my sample date was, just so I can see things together as I'm working here. So I'm going to click on year, drag, and bring it over. Okay. Now one thing is this doesn't permanently change the order of the columns in your data set. If I remove this data and I added it again, the default columns would have these at the end. But just for now, this helps me to see what I'm doing. So our first step was to populate this temp column, so I'm going to right click and go to calculate field. We're going to fill it with the sample date, so I'm going to find sample date here. Here it is. Double click. It shows up in here. Temp is going to be equal to sample date. Hit OK. Alright, so now I see my sample date is filled with, my temp is filled with my sample date. So now I'm going to populate this year by ripping off these last 4 digits. So right click and go to calculate field. And here we're going to do a little Python coding. So what we want is we want to grab our temp field. So go down here and find temp. Here we go. So there's temp. And so now you want to type in there bracket -4 colon bracket. So it's ripping off the last 4 digits of this temp field. So we should be left with something that says 2015. So we'll hit OK. And it looks like it works. Let's sort here by our date. Both ways, sort descending. Okay, 2014. Sort ascending. 2015. So woohoo! It looked like it worked. So now we have a column called year. And now we can delete this temp field. We don't need it anymore. So right click and delete. Okay. Okay. Alright, so now it's time to explore our data. So I want to make this symbology based on years so I can see the different colors for different years. So right click and go to symbology, and under symbology select unique values, and for this field select year, our new year column. So I'm going to double click on this 2014, and I'm going to go to properties, and I don't know, I'll make it blue. And I'm going to change the outline width to be 0.04 and make it a little bit bigger. There you go. Now I'm going to go back arrow up here. I'm going to do the same for 2015. Let's change it to red. You can change it to whatever you want. I'm going to change this to be 4 and make it a little bit bigger. Yeah. So 0.4 and 5, and I'm going to make it red. Alright. So I can see my points, like here I can see, okay, we had some samples in 2014, but it doesn't look like it was sampled in 2015 in this area. Okay, so as before with the water quality for the state of Alaska, let's look at charts, for our data, get an idea of what it looks like. So we can either have this layer highlighted and go up to data and go this way, or you could right click on this and you could go to create chart. So let's create a line chart. Alright, so like before, we've got to select variables in the chart properties pane to begin. Okay, so we want to choose our date, sample date. For the aggregation this time, let's do none. We want all the data points used. Okay, and for the numeric field, it's going to be our measured value. Hit apply. Okay, so we can see there's some seasonality to this. In the winter, when it gets cold, you have higher dissolved oxygen. The water's colder, it can hold more oxygen. You don't have as many creatures using the oxygen in the winter. And then in the summer, you see that there are dips in the dissolved oxygen. One thing, some neat things about this, since we do have a lot of data here, is I can zoom to the entirety of the Chesapeake Bay, and let's say we were interested in whatever these points here are. So if we click and draw a little box around them, it highlights them, and I believe this one got highlighted. So let me click off of it and watch it highlight this. Yep, so right here is where we see like a really high value in 2014. So the nice thing about this is you can look at your data and it's linked and you can figure out what's happening where. One of the other things about this data, since these are linked, is what if you only wanted to look at the northern part of the Chesapeake Bay? You didn't care about the other part. So you can go here. I'm going to hit clear up here because I still have a record selected, or I can hit clear here. Okay, so since it's linked, I can say just show me the extent. I don't care about the rest of the Chesapeake Bay, just show me the top part. And there, these data points here are all for up here. Nothing in the other part of the Chesapeake Bay. So you could limit your chart making to a specific geographic region. So if I zoom out, it's going to update the table. You see there's more and more. And now we're back to basically the full entire data set. So I'm going to turn off that extent. To toggle these on and on, off and on, sorry, you just click the buttons. Okay. I wonder what rotate chart does. Okay. Looking at it. I mean, you can kind of see the shift downward here in the middle of the season. But personally, I think the other way is better. But, yeah. Alright, so we have our chart. If we go over here, we can change this aggregation to mean, and you'll see Now we just kind of have a more smoothing pattern of what's happening, and you can change the interval time too if you wanted to. You know, if you're interested in doing it, say every 2 weeks, you can change it and it'll smooth your data out. Okay, so those are some things with the chart. We have a lot more data, so there's a lot more cool things we could do. One of the things I want to do is I'm interested in what is the mean dissolved oxygen in 2014 versus 2015. So for that, what I'm going to do is I'm going to do a histogram. So I'm going to right click here, and I'm going to go to create a chart, and I'm going to say histogram. Okay, so it's asking for variables over here, so I'm going to pick the measured value. I'm going to put it at 64 bins. Okay, and so here's what the histogram looks like for dissolved oxygen. It looks pretty normally distributed. Before I move on to that, one thing with this chart is I'm going to go and change this back to the 5 days here, so what we had before. And I'm going to change it back to no aggregation. Okay, I would like you to, one of your questions is to make the graph like this. Use something besides red and blue and submit it within your homework assignment, just so I can see that you can make a graph. So please remember to make this graph. Alright, so now we're on to the histogram. So we have our histogram, going back to it, and the dissolved oxygen for the whole data set is 7.5. So that includes both years, and it's pretty normally distributed. You know, it's the mean and median are pretty close together. And so one of your questions is, what is the dissolved oxygen for 2014 and 15? One thing that you can do is you can look at the attribute table and select by attributes. So only select 2014 data. So I'm going to go here and go to year is equal to 2014, and then hit OK. Okay. So now we can see that there's 12,359 records selected. I'm going to hit this show select records, and I can see that indeed it's 2014. So I'm going to go back to my histogram, and I can see where the 2014 data is highlighted. You can see it's colored here. So if I only want to show 2014 to get at what is the mean for 2014, I click this selection filter, and so now it's only showing me 2014 information. So see, the mean is changed, so this is the 2014 mean. And in order to do the 2015, you know, you would go back and you would change the selection here. So what I would do is you could go up to table, and you could say select by attributes, and instead of 2014 it's 2015. Hit OK, and now we see we have 2015 records selected. Go back to your histogram, and I'm going to toggle off the selection. So now we have 2015 selected and 2014 here. To only show 2015, hit the show the selection, and so this is the 2015 mean. So I ask you in the homework assignment to write down what is the answer there. All right. So I'm going to clear everything and close things down here. Okay. So now we get into the really fun stuff, is doing this spatial interpolation. So there's two main approaches to this. It can be deterministic or geostatistical. So deterministic is you know, a little bit less robust. Basically, you're creating a surface from measured points, which in our case is, say, those dissolved oxygen points, and you can use inverse distance weighting or a degree of smoothing that looks at the nearby values and then tries to create a smooth surface. So in this case, like a smooth surface would be a raster. The geostatistical interpolation technique, kriging, is very popular. Kind of tries to reduce the error when you're doing your prediction. So it's trying to predict the values and do a model in the background that reduces the error in your predictions. So you can think of it, you know, when you're doing linear regression or general linear modeling. You know, you can build a model, but if the error is so high, it's not a very good model and you probably shouldn't use it. You want to build a model, you know, that fits the data properly, and that's what these geostatistical techniques do. And they're all kind of leveraging this idea of this autocorrelation. So points that are nearby are going to be more similar than points that are far away. And one of the ways that they assess this model performance is something called cross-validation. And cross-validation, you know, is a leave one out resampling method that first uses all the input points to estimate your model, but then starts to remove single points and then looks at the error. So it's almost like a Monte Carlo simulation, if you're familiar with that. So take a data point out, do your model, see how well it fits, take a data point out, redo your model, see how well it fits. And in that process, it's trying to lower your root mean square error. So it's computationally intensive, which ArcGIS does take a powerful computer. But first, let's try this deterministic method. We're going to use something called global polynomial interpolation, GPI. It's a very quick method. It's not going to take very long to run, and it's best used for surfaces that change very slowly and gradually. There is no assessment of prediction errors, and it will often be too smooth. So this isn't one that I've ever used, but yeah, it runs fast and it'll allow you to see the difference between various methods. And so I'm just going to remind you again that in this Word document I have some of the steps laid out. They don't follow exactly with the video. It's okay. Sometimes, you know, like I mentioned, there's many ways to do something in ArcGIS, but it will have some questions for you to answer as you go through here. So let's do the GPI. Alrighty. So we have our point file here. So to do this, go up to Analysis, and you'll see Geostatistical Wizard here. Click on that. And what you want to choose is this global polynomial interpolation. So we want to choose our dissolved oxygen. The data field is our measured value. Okay. And then hit next. Use the mean. Alright. One thing about this is, since it's not really running a statistical approach in the background to estimate what is the best parameter, we just kind of have to play here. And so this surface looks very similar. And you can kind of see a little bit of a different yellow here versus here. So we changed the order of the polynomial. So basically this is making the model more complex. And you can see, oh, now we start to see some differentiation. It's pulling in more information as far as what is the dissolved oxygen at each of these points. Even more complex. Oh, even more. Okay. I'm already looking at this and thinking, this is really weird. Why is it predicting a huge red area here when there's really no points over there? Okay. And I mean, if you go to 9, it's like, ooh, abstract art here or something. This is way overfit. This model's completely overfit. You can see it's snapping very closely to these points. And so let's just go with 4. It's kind of in the middle. And then hit next. Alright, so this is kind of your most important table, your cross-validation screen. And so this shows you your predicted versus your measured. So it's showing you what your output is going to be compared to the real data. And what you want is you want your reference line and your regression line to be close. And for the most part, you know, it is in the center, but when you get towards the end points, it deviates. So in this example, when the dissolved oxygen is low, the model tends to underpredict what the dissolved oxygen is. So if the dissolved oxygen in the reference line, so that's the real data, is, let's say, 4.6, the model is going to predict that it's going to be 5.5. And then when we come to the other extreme, the model tends to underpredict. So if the real data said that it was 9.8, your prediction is going to be lower, like 9.37. So it's a bit off. And we can see what our root mean squared error is right here, so that's very important. One thing when I'm doing a modeling like this is I typically take a screenshot of it. So for Windows, it's the Windows key, Shift and S, and that pops up the screenshot. And so I just copy this center here, you can see. And then Paint is a program that I use. So I'll close this down because I was working on it yesterday. If you don't have Paint pinned, you can go to the window here and just type Paint, P-A-I-N-T, and there it is, and hit enter, and Paint pops up. Now you can hit Control V, and there it is. And I'll just crop it. So we've saved our results here in the background to come back and look at later. So I'm just going to minimize this for now. Okay, so here is our root mean square error for our GPI. And I ask you what that is. But okay, so now hit finish. And you'll have just a little report that pops up. And hit OK. And there you go. There is your surface using the data that's in these points. So notice it's a continuous surface here. One thing that's a little odd is that it's predicting dissolved oxygen on land. Clearly that's not right. So we have to do some post-processing of this data. So one of the first things is when you're doing this type of work, these files that get created are often temporary files. So they're not really stored anywhere. I've been burned by this before as I go back and I want my, I made my Krieged map. And it's not stored anywhere. It's just kind of temporary within the program. If you're familiar with R, it's kind of like a scratch workplace. So you will have to save any product that you want. If we go and we look, see the source is telling me that the source is a shape file. Clearly this is not a shape file. So it does need to be exported to a raster and saved. But first I would like to try and see if I can clip this out so that we're not predicting dissolved oxygen on land, because that doesn't make any sense. So when you use polygon files, vector files, polygons, points, lines, it's called clipping. When you do that same thing with a raster, it's called a mask. So go up to Tools and search for mask. And you'll see you want this extract by mask. It's in your spatial analysis tools. So down here. So double click here. Let's see if we can drag this over. And so we can't. Because, as I mentioned, even though this looks like it's a raster, it's really not a raster. It's a temporary, very awkward data file. So we can't do this just yet. Basically, see, it does not exist, even though I see it with my eyes. So what we have to do first is we have to save this. So right click on it and go Export Layer and go to Rasters. So we want our output raster. I'm going to click here on the browse and navigate to our folder. I'm in our folder. And I'm going to call this GPI let's see, GPI. I'll just leave it GPI because that's what it is, and leave everything else the same, and then hit run. Okay, so now we have our data, and now I'm going to do the mask. So I'll go back over here, and if you don't see it, you can type mask up in this search box, or I can see that it's still highlighted here. So now I can double click on extract by mask. I can actually choose my new mask. I'm going to mask it by the Chesapeake Bay, and again I'm going to click on my folder here, and I'm going to say GPI underscore mask and put .tif on it. We'll make it a TIFF file, which is a type of raster. And you can extract inside or outside. It makes more sense. We want to extract inside, so inside where the water body is, okay? And then hit run. All right. So I'm going to turn off the old one. And now I'm going to turn off the other old one, and we just have this. So it's clicked to the border of the Chesapeake Bay. So let's change the symbology. Right click on it and go to symbology. And let's try to match what we had before. So let's go down to classify, and let's say 10 classes. And then let's try to find the color scheme we had before. So it was like blue to red. Scroll. Right here it is. Okay. So basically this is telling me that we have higher values of dissolved oxygen where you have the red, and you have lower values of dissolved oxygen where you have the blue. You know, I always like to double check these and see what's going on here. So technically these values here where you see the red should have the highest amount of dissolved oxygen. So I'm going to open up my attribute table here so I can see both, and I'm going to sort by dissolved oxygen. I'm going to put the higher values up at the top, sort descending, and so I want to select these values, so I'm just clicking and holding my mouse and just want to see where they pop up. Interesting. Or here and here. So in order to see it better, I'm going to go to symbology. I'm just going to do a single symbol. Now I can more easily see, okay, here's a high, here's a high, here's a high. You can see the coloration here, there, down here. It's not really matching up with the red here. So I'm not really happy with this at all. This one's high, but it's actually in kind of a low prediction area. None of these up here, which are supposedly high, are highlighted. I also want you to now add a different layer. So go into add data, and I have created for you this station summary. So add this stations O2 summary. So what I did for you here was I calculated what is the mean dissolved oxygen for every station. That way we can also more quickly visualize the accuracy of our results. So once you got it added, let's go to symbology, right click symbology, and now change this to graduated symbols. And so now the larger colors are actually bigger, and the smaller dissolved oxygens, but we got to first check mean here, sorry. So mean, make sure the field is the mean. And so the larger values are higher dissolved oxygen, the smaller symbols are lower dissolved oxygen. One little cool thing with this is you can actually match these colors to the colors that you see in your ArcGIS Pro. So I'm just going to clear everything. And so if I click on this, if I could hover over the symbol and I right click, I can go to eyedropper. And so now I can actually combine size with color. So if I want high values to match my raster, see how my little eyedropper here shows up, and I can hit click and it fills it in. Say I want the low one I right click, go to eyedropper, and now let me try to find, oh, here's the lowest value right here. Okay, let's do the moderate one, right click, eyedropper. Let's go with this orange here. Let's go the second lowest here, right click, eyedropper. Let's go with this, how about this color? And then the middle eyedropper, let's go with the yellow. There we go. So it's a way where you can help standardize your colors within your maps. And so now I can see, let me close this down, I can look at this, and if I turn off my raster, I can see, okay, we've got some high values along the shore here, up in this bay, and there is a couple up here. How does that compare with my raster? I'm looking at it. So I do have some larger values. It's driving the reds I see over here. I have some larger values. It's driving this right here. I'm not sure why I have a red tip down here. Not making a whole lot of sense. And this being really light blue is not making a whole lot of sense either, given that I don't have some of these light small blue data points down here. So I'm not really impressed with the fit from this model, but no worries, let's try a different model. Okay. I guess one of the other things before I move on that you can do is you can go back to that histogram tool and say if we did want to make a histogram of this. Remember how with the histogram, let's choose our number is going to be our mean here, and the bin I'll put 64. Remember how we can select our high values here, so we can figure out where we're actually getting the high values on our map and try to compare it. So you can see these circles that are highlighted here. These are the top values for dissolved oxygen, and they should be in areas where you do have red. And say for this one, it works pretty well. We can look where's our lowest values here, so we can click and select these, and our lowest values look like they're right in the center. So this is another way where you can combine kind of these charts in ArcGIS Pro and see how well your model is fitting. So just another little tip. Here's clear. All right, and clear. So I ask you to tell me what you think about your map. Now we're going to try a different approach here. So I'm going to turn off the summary one, turn off our GPI one, and collapse it, kind of keep things clear here. Turn back on our dissolved oxygens, go up to analysis, and let's go back to our geostatistical wizard. Alright, so this time I want to try this kernel interpolation with barriers. So with barriers means that we can actually skip the whole masking process and include the Chesapeake Bay boundary within this analysis, so we don't have to do that additional step. So our data is going to be the dissolved oxygen, and measured value is our field. Our barrier data set is the Chesapeake Bay, and then hit next. Use the mean, hit next. Okay. Alright, so we can see that if this has a bit more statistics to it. It's decided that this fifth order polynomial is the best fit for this data, and our output surface is going to be our prediction. The bandwidth, you can click here to optimize. I'd like you to do that. So it's figuring out what is the best distance to look for. So if I hover over bandwidth here, the maximum distance at which points are used for the prediction. So it doesn't want to go too far, but it wants to go just far enough. And you can see the bandwidth size right here, that circle. That's how far. So these data points within this circle would be used to do your interpolation for the smooth area you see within this circle. All right, so hit next. Okay, and we can see here's our cross validation. We can look at our model fit. We see our root mean square error right here. Now if I put this to the side and I bring up that paint we had before, root mean square error here is 0.78. Over here was 0.85. So we want a lower root mean square error. So lower error. Right now our kernel interpolation is doing better than our other approach, than our GPI. This value is higher than this value. Okay? So I'm happier. We can look at the error here, and you can see that I'm just looking at the errors on this axis. It's pretty balanced between lower and higher values. So when the dissolved oxygen is low here, like 4.6, it tends to estimate what the dissolved oxygen is, and when it's high, the dissolved oxygen is high, 9.8, it's tending to underpredict what the dissolved oxygen is. And I mean, you can look at the distribution, you can look at measured and predicted and see some pretty neat charts here to look at. Look at that. And the data is pretty normally distributed, so that's always nice when that happens. Okay, and this table over here allows us to look at the errors, and you can see what point has the highest error. So the most underpredicting is happening with this data point, which clearly is here at the bottom of your chart. And then if we sort the other way, you can see where your errors are. So this just will give you an output table if you wanted your standard errors, your predicted value. So this, in this example here, the measured value for that point is 0.46. The model is predicting 6.99 for that data point. Okay? So then hit finish, and again it gives you this nice summary, and hit OK. Alright, well, we can see, yay, it's already snapped to the boundary of the Chesapeake Bay. We don't have to go through all that hootenanny of clipping it, masking it out. And just like before, we need to save this as a real raster. So right click on your kernel interpolation and go to export layer and to rasters. And again, the prediction, navigate to your same folder. And this time, I'm going to call it kernel interpolation.tif, and hit save, and leave all the rest the same and just hit run. So we're saving our output now, our prediction, because this other one is just a temporary. Alright, so here is our new map. Okay. I'm looking at it. Let me turn back on our summary. Feel free to explore. I can see again, you know, we have higher values up here. This one, you can see this is red because of this higher value. Again, this tip is, you know, a little bit red, but it's pulled in the lower ends here, so you can see this isn't solid red. Alright, so one way to kind of compare this kernel interpolation with the GPI mask is turn them both on. Let's see if I can get this to work. So with the kernel interpolation still highlighted, let's go up to, let's see, view. I gotta try to find it here. I always forget where it is. Go up to raster layer. So raster layer and then hit swipe. And so see, you have this arrow that's here. So if I click and I hold, when I'm going, basically I can see the GPI layer as I scroll down. So right now the kernel layer is on top, the GPI layer is on the bottom. So you could sit here and click these on and off and try and look at the differences. But one way is if you have this swipe, you click and you hold, as I drag down, it's turning off that top kernel interpolation layer and allowing you to see what the GPI one looks like underneath it. So we can see how the two look. So the kernel one, notice how it better captures the blues here. Remember we had a whole lot of lower values along here? The GPI doesn't capture that at all. The kernel is much more heterogeneous. I think it captures the the variation within the dissolved oxygen for the region much better. So I'm more impressed with the results from the kernel interpolation. All right, so I would like you to put what is the root mean square error for the kernel interpolation into the document as one of your questions. Okay, so another interesting thing that you can do with this data is, because you have a nice time series and you have a nice spatial coverage, you can do a space-time analysis, which is pretty neat. These are also useful for looking at car accidents, maybe boating accidents, you know, anything where there might be a space-time component to it. And so basically we're going to be building what's called a space-time cube. So you have time and you have space, and we're going to be looking at how those both vary across time. And it's a two-step process. So if you're interested and want to Google more, it's a space-time analysis. Again, looking at, you know, X and Y, lat and long, and then across time. Okay? And so we're first going to start by creating a space-time cube by aggregating our points. So kind of bringing our points together. Okay. So first we're going to want to add this other point layer that we have. Move this to the side. Okay. So add data. And add this 2016, 2022. Okay. Turn these other ones off. Okay. So we have this new data set. So now go over to, if it's not visible, go down to Tools, your Geoprocessing. And you'll see this space-time pattern mining tools. So under Toolboxes, go all the way down, and you'll see Space-Time Pattern Mining Tools, and you'll see Space-Time Creation Cube. Double-click the top one, create Space-Time Cube by aggregating points. It might take a little while. Alright, your input feature is going to be that point file we just added. Okay, so store your output space-time cube in your folder. So my Chesapeake Bay folder, I'm going to call it Chesapeake space-time. So Chesapeake _ space _ time, and hit save. My time field is going to be my sample date. Now, you know, back at the start I mentioned it's important that your field is recognized as a time field. Since it was recognized as a time, and specifically a date field, it automatically knows, hey, this is the field we want to use. Okay? So for your time step interval, I want you to put 2 weeks. So this is kind of, you know, how many what increments are we going to look at through time. And so you want to have enough data points within your time window in order to run the model. If I put this as, 2 hours, it's not going to work. We are not collecting data on a sub-hour sampling rate. So you've got to think about what is your sampling rate. Am I surveying moose, every year? So then maybe your sampling frame might be 5 years, like moving average of 5 years. So think about your data. All right. So, and I really like the hexagon grid. I think it's more natural than the fish grid, which is just basically blocks, squares. Hexagon is more, you're going to see hexagons form within our study area. I just think it follows more the natural boundaries of features. And so down here for our distance interval, let's put 10 kilometers. Again, you kind of got to just play with your data and know your data, how big your study area is. And for our field, we're going to choose measured value. For our statistics, let's choose mean. And let's fill the empty bins with zeros. So in this case, we know that there are no zeros for dissolved oxygen. So basically where we have zeros, it's kind of like no data. Okay? So once you have all of this set, let's hit run. Okay? It says it's completed with warnings, features bad records. That's okay. I mean, there might have been some things wrong with it. Reading 2 of the records out of 12,000. I'm not really concerned that I couldn't read 2 records. So we're okay with that. All right. So now nothing popped up here, but we need to go back to tools here. And now we actually need to create the visualization. So we need to visualize our space cube. So now let's go down from space cube creation to space cube visualization and hit the 2D, visualize space-time cube in 2D. So now you have to remember where you saved your space cube. So we saved it to our C Chesapeake Bay, and hit OK. Our cube variable is going to be our measured values, not our count of the number of sample sizes we had. And your display theme, let's say trends. We want to see the trends. Okay? And we'll just allow this to go to the default location. But I'm going to shorten this and say Chesapeake Space Time Cube 2D. So this is what it's called, just going to your default geodatabase. And then I'm going to hit run. Okay. So now we have a statistical method, because this is all based on statistics, to explore where over the 2016 to 2022 time period, where we've seen an upward trend in dissolved oxygen, this purple here, based on 99% confidence. So that would be, a p-value of 0.01. So very confident that the dissolved oxygen is increasing in those areas. And then you see along here, the dissolved oxygen has been decreasing with high confidence. Something is going on along here to decrease the dissolved oxygen. Maybe there's agricultural runoff over in here. So they need to look at what's going on in this area to create a declining trend in dissolved oxygen, which is, getting back to it, not very good for the fish and the creatures. And in the middle here, we have kind of no change in dissolved oxygen. So this is a way to, look at what are the hot spots, for changes in your values. Akitan has the Trident seafood plant. This would be a way that you could look at what is the dissolved oxygen, within the bay there, and how has it changed over time. Okay. So we are going to do another statistical example to look at trends and changes in dissolved oxygen. one thing that we can do is something called an emerging hotspot analysis. So I'm going to go back up to Tools, and here I'm going to delete mask in the search, and I'm going to put hotspot. Okay. All right, I see my emerging hotspot analysis. So her emerging hotspot analysis, it identifies trends in the clustering of point densities or values in a space-time cube created, within ArcGIS Pro. So let's click on that, and we can see we're in this space-time pattern analysis. So now we're using that space-time cube that we created, and we're going to look for hotspots. So let's double click on it, and it wants our space-time cube. So let's navigate to our space-time cube that we saved in a known location. All right, our analysis variable is going to be our measured values, mean zeros. Okay, and again, I'm just going to shorten this so that it's Chesapeake Bay Emerging Hotspot Analysis. All right, and for the relationship, I'm going to do K nearest neighbors, and it shows an optimization of 8 spatial neighbors. And if you're ever curious, you have little icons that pop up here where you can read more about what these different options are. Again, when you come to do, say, your analysis, you'll want to look into these and figure out what's best for your data. And our polygon mask is going to be the Chesapeake Bay. All right, and entire cube, so we want to use the entire cube here. All right, and then hit run. Okay, so you see there's a lot more variation in what this model is looking for. So it's a lot more, a lot powerful, maybe potentially a lot more insightful. So I'm going to turn off this space-time cube. And looking at this, so the white areas are basically no real pattern detected as far as, emerging hotspots. However, there is sporadic hotspots here. So some years these areas are high, some years these areas are low. I might look into seeing what years were high, what years were not high, and seeing if there's some type of relationship there, correlation between what drives some hotspots in these areas. But based on this emerging hotspot analysis, in general, the places to watch out for are these 2 areas. The hotspot, analysis more gets into, trends. You can have a gradual trend, gradually increasing, gradually decreasing, whereas the hotspot is kind of looking for more abrupt changes, which is one of the reasons why you're like, oh, well, we saw some trends, with our space-time cube. Well, these can be gradual changes over time, either increasing or decreasing, whereas this hotspot is like, okay, something's popping up here. There's more of a variation in your results. Okay? All right. All right, so the last thing that I want you to do now that we've done all this analysis is, some practice making a map. And so to make a map, we're going to make a map that shows our 2 different kriging approaches, our GPI, or interpolation approaches. Our GPI, not deterministic, and our statistical one, the kernel interpolation. So go up to Insert and New Layout and choose this letter landscape. Okay. So what we're going to go for is we're going to want to have the GPI on the left and the kriging one on the right. So go up to map frame. Actually, don't go up to map frame yet. So one thing that I would do is I would actually insert another new map. Insert a new map. And now take this kernel interpolation and drag it to this new map. There. And then double click on map 1. Slowly enough to get a change and call it KI. Alright. Now insert a new map. Another one. And now drag the GPI to that one. There we go. And drag it over here. And now double click on map 1 slowly and rename it GPI. Okay. Oh, sorry. GPI. Okay. Alright. So now go back to your layout. And now we'll go up to map frame and pick your GPI one here. And then draw a box roughly halfway. Let's see. Let's go to 4.5. There we go. Okay. And then go to map frame again and now grab your KI one and draw a box over here. Okay. There you go. So now you have the two boxes. Alright, so click on your map frame and go up to map frame properties here. And we want to make sure that these two map boxes are the same. So when you click on map frame properties, you'll see size and position over here. Let's try to change these to, let's see what 4.5 looks like. And we'll put 6. Okay, so that works. We can go over here, click on this one, and again go to map frame, and then put, what is it, 4.5, and then put 6. Okay, so now we know that these are exactly the same height. Okay, and we can click, and then hold down the shift button and click, and then go up to align and say align top. So now that we know that these are both aligned on the top. I'm going to go over here and say zoom to layer. I'm going to go down to the GPI mask one, right click and go zoom to layer. And so now they both have the same zoom. Okay. One thing is that this Esri text can get in the way. This is the default credits, service credits for the layer. One way that we can deal with this is we can go up to dynamic text. And we can go down to, here we go. Right here, service layer credits, click on that. And then draw, just draw anywhere on your map. And there we go. See, now they're gone, but they're still here. So now with this highlighted, I have my, 4 arrows there. I can right click and I can go to properties. And I can go to text symbol, and then I can go to appearance, and I can make these smaller, like 6, and I could make the color a little bit less obnoxious, make it a light gray, and then hit apply. There, so it's still here. I can click on it and I can move it a little bit, and I can drag it down here, but it's not as obnoxious in your face in my way. Alright, so one thing, if I wanted to make these equal, I'm looking at my map here. Layout, grid lines and rulers are there, so I'm looking up here. Don't really want it to be that close, so I'm going to add a grid line, and so I did it at, this 1, 2, 3, 4 from the edge. I'm going to go over here and I'm going to do the same thing and add a grid line right here, or add a guide. And so I want to kind of snap this over to there, and snap this, click on here and move it so it's kind of snapped to there. So again, I'm going to have to realign the top of these, so shift, they're both highlighted, map frame, align, align top. So now they're snapped. But now they're both equidistant from the end. Okay, so now we have our two maps. What we need to do is we need to add some text. So we need a title and things like that. So we're going to go up here and go to text. So insert, we have this text graphic. I'm going to draw a big box here. Okay, so now we can just start typing. So I'm going to highlight this and say dissolved oxygen levels in Chesapeake Bay. Okay, and this is way too small. We can click off of it, but we can click and we can see over here text box 1 is there. We can see it here. I don't think I'm ever going to be able to spell Chesapeake right. Alright, so text symbol, and let's make this a 36, and let's make it bold. Hit apply. So that's pretty big. Let's see. I'm going to look at the position, and I want it to be centered. Okay, hit apply. Okay, so Chesapeake Bay, and I think it's a little bit too big, so let's go back up and let's change it to 28. Okay, and then we can make this longer. And what I'm going to do is I'm going to align my box here with this 1-inch mark, and I'm going to align this box over here with this 1-inch mark. That way it's kind of centered from left to right. I'm just going to make this smaller here. Okay, so now we have Chesapeake dissolved oxygen levels in Chesapeake Bay. Okay, so now we need to have some titles. This was our GPI one, and this was our kernel interpolation. So again, we can go back up to this text, and we can draw a box over here that says GPI, but never use acronyms when they're not spelled out. So I'm going to go back to our Word document and capture what exactly that is. So, oops, global polynomial interpolation. So I'm just going to copy it here and then come back over here, highlight and paste. Okay. Alright, click off of it. So that's a little bit too small. I can see that my text box over here, here it is. So I can go up to text symbol and I can change it to, let's try 18. And again, I'm going to want to position center. I'm going to hit apply. Now this red dot means your text is too big for your box size, so I'm just going to make my box kind of go all the way across the width of that. So I mean, that looks pretty good. Alright, one little tip and trick, a hack that you can do is you can select this box, right click, and you can say copy, click anywhere on the document and hit paste. And now you have the exact same formatted box created, but we can move it over here. And I can come over here, and this was our kernel. Interpolation. Okay, and click off of it. Alright, click, hold your shift, click, and let's see if I can align these, and not seeing the option. There we go, align top. So there we go. So what I did was clicked, shift, clicked, and then went up to text here, and with the text then you get the align and align top. Okay, alright, so now we have the kernel interpolation. We need to add a north arrow here. So to add a north arrow, go to the north arrow and pick whatever you fancy. Doesn't matter to me. Put some own flair on yours. So I'm going to put an arrow right here. There we go. Now we have a north arrow. Okay, so now comes the tricky part, is the legend. We really don't want to have two different legends between these maps. It'll make understanding these maps difficult. We want them to be on the same scale. So let's go over to our GPI mask and go to symbology. And let's choose defined interval I don't want 3. So let's try equal interval. And let's try 7. See what this gives us. Okay. So I'm looking at this and seeing that our range of values is like 5.3 down to 9.1. Our range of values for this kernel one over here is 5.4 to 10. So we're okay for this upper value. We're okay for right here. But for this upper value here, I'm going to change this to 11. Because that way it'll capture. If we apply the same symbology, it'll capture here. I'm going to change this one here to, let's say, 8.5. This I will change to 8. 7.5. This I'm going to change to 7. This I will change to 6.5. And this I will change to, let's say, 5.5. Okay. All right. So for our labels, remember we don't need to have endless decimal points here, so I'm going to go up here and change the format data labels to 1. Okay, go back. So here's our labels. So now we got to create the exact same symbology for this kernel interpolation. So click on kernel interpolation symbology. And let's do, I believe it was equal interval. We changed it to 7. Okay. And so now change this to match. So let's put 11 there. Here I believe was 8.5. This is always really tricky to do. So this I'm going to change to 8. See if I can do 8.5 for here. Okay. Now I'm going to change this one because it's acting very oddly to 7 for now. Change this one to 8. Okay. I'm going to change this bottom one here to 5.5. This one here I'm going to change to 6.5. This is 7, that's correct. This one I'm going to change to 7.5. Okay. So now this is what this should say. I'm going to go up here and change our data labels down to 1 again. Number of decimal points. So I'm comparing this to what I have here to see if this matches. And the color scheme is a little off. I'm trying to figure out what's going on here. Because this color should actually be an orange here. So what I'm going to do is I'm going to right click here and say format symbol. I'm going to do the eyedropper and I'm going to choose this color. Right click here, format symbol. I'm going to choose the eyedropper and the next color. Here, format symbol, eyedropper, we want the next yellow. Okay, here, format symbol, eyedropper, and we want the next green, I believe. Okay, and so now I'm looking at these two, and they look identical. And the reason why we want to have these identical is that then now we can just use one legend and they're comparable. So when they're looking at this red here, they're the same, 0.86 to 11. So now we've achieved our goal. So now we can go up and click on legend and then just draw here in the center. Click and drag. And now we see our legend. So we see a legend up here that is formatted. Expand this. And click on a kernel interpolation, because that's actually the legend that it's using this kernel interpolation layer to draw the legend, but it's fine because it applies to both of them. Now we'll go to properties. And let's click off of the layer name. Okay, it disappears. Let's go to indents and let's indent it a little bit, the classes. So change this to 15. See how it's indented? Okay. And now come back over to your kernel interpolation here. And instead of value, let's click on it and click on it slowly, put dissolved oxygen. Try mg-val. And hit enter. Alright, so I'm going to click on, and I'm going to click off, and now it's updated here. So now we do have it. Just playing around here. One thing is we're kind of constrained by the size of this. So this is one way that you can get this dissolved oxygen here. But you notice it's not wrapping. When I move it, it doesn't wrap. So this is where you kind of got to be creative when you're making maps here. So what I'm actually going to do is I'm going to go back up to my legend and the kernel interpolation here, and I'm going to take it off. And I'm going to actually just add it as a text. But first I want to make these numbers bigger because I'm old and I can't really see them. So if you go over to legend, you have this drop down, and what you want to do is you want to edit the labels of this layer. So go to labels, and let's make these size like 18. Let's try that and hit apply. Okay, so now they're bigger. It's okay that this box overlaps with here because there's nothing to this box. You know, it's not going to show up. Our goal is to make these labels as big as possible for people to see. So there, I can center it in here. I'm going to move it down a little bit. And now I'm going to put that dissolved oxygen right over in here. So I'm just going to go over here, double click on this, copy it, Control C, come here. I'm going to insert text, draw my box here, and then paste the dissolved oxygen in there. Click off of it, go over here to my text symbol to make it bigger. Let's see if I can make it 16, and I want it to be centered. I'm going to hit apply, and I'm going to go back over to my element up here, and I can actually wrap this text now. If I hit enter here, I can put the milligrams per liter on the bottom. So hit enter, then just click off of it, and you see it updates here. Okay, so it's looking pretty good. I think I actually want this bolded. Let's go back over to the text symbol and go to bold and hit apply. Alright, I'm going to bring this down a little bit. I'm going to click on this box and drag it down. Click on this dissolved oxygen, bring it down. Okay, so now we can see the differences in each of the statistical methods based on for dissolved oxygen. The last thing I want you to do is add your name to it, so you'll need your own unique name. So maybe just right in here, draw a text box, and I can say by Jen Schmidt, and then put created. Today's date is May 16th. So put your own date. Alright, so here we have this. I'm actually going to go to the text symbol and just center it because my OCD. There we go. Okay, so now we want to say send this to people and say look at my cool results. And I would like you to attach this picture. You could either put the picture within the Word document where you have your other questions answered at the end. That would probably be the best, but if you wanted to also submit it as a JPEG, you could do that. So go up to Share and go up to Export Layout, and I would choose JPEG. Here you can have your quality, the higher the resolution, the better the quality, but the larger the file. If you're publishing in journals, they usually ask for 300 dpi, so that's why mine is usually set to that. And so click the folder, and now navigate to your folder where you saved everything, GIS. Actually, it was a C drive. C, GIS, Chesapeake Bay, and I will call it, I'd like to use your name, so for me it'd be Schmidt, DO, dissolved oxygen, poster, and then just hit save, and then don't forget to hit export. And so it's exporting that as a picture, and so now I can go to my Chesapeake Bay folder here, GIS, Chesapeake Bay, and sort by date modified, and here it is. I double click on it and I can see my own poster map that I made. So in your water quality example, oops, not that one. I'll get it right here. You could go down to the bottom and you can insert. Just make this bigger for people. Insert picture, this device, and then go find your map. Oops, sorry. And insert it there. So with your name and the date that you created your map, and then upload your exercises and you're done. All right, that's it for this week. I know we covered a lot, but you covered a lot of good things. Spatial interpolation, doing kriging. These space-time cubes are pretty powerful tools that ArcGIS has. So thanks.